All right, today we're going to be talking about water resources. Water is a big issue. We need water every single day. And as you can see from this figure, even though we're considered the water planet, there's not a whole lot of fresh water that we can actually use. 97% of our water is sitting in the oceans, and so it's salty. We are not necessarily able to use that for drinking, showering, industry, things like that. So when we look at the amount of fresh water that's on the actual planet, it's not even 3%, really, really small percentage, which causes a lot of issues as to where are we going to get all this water that we need. And even out of that 3%, 77% of that 3% is sitting in ice and glaciers. And so we can't access that either. So we're really, really limited. We have about 22% that's sitting in our groundwater. We do pull from the groundwater, which causes some other issues that we're going to see here in just a minute. And then a very small percentage, less than 1%, is in our rivers and streams, which is much easier to be able to access and utilize. Okay, so some vocabulary. Groundwater, what exactly is it? Well, groundwater is basically, we call it also our aquifers. It is a space between the soil and the rock and the sediment underground where water resides. And you can see from this picture here, down here is some groundwater, and we have some more even further down. We also refer to this sort of as the water table too. You might have heard about that. Basically, the water table is the top line here of this aquifer. The point where as we start drilling down into the ground, we start reaching that aquifer, that containment area of water underground. And then we have this really important word called recharge. A recharge area is if it rains, and this rain percolates down through this soil and this ground. It's the area, the space that where that percolates down through, all that water ends up in your aquifer. Okay, so you can see in this figure, we actually have two different aquifers here. We have one that they're calling an unconfined, which is this top one, and then a confined. So the difference is, an unconfined, the soil that sits on top is really porous, lots of space. The water runs right through it, right down into the aquifer, and keeps this aquifer filled. Really simple, easy to access. We also have confined aquifers, which are a lot harder to deal with because the layer that sits on top of them is impermeable soil. Okay, so probably a lot of silt, a lot of clay, and water just doesn't flow through it very easily or almost at all. So even though this aquifer covers this whole area of ground up here, that water is not getting down into it. There's only this small little recharge area where it actually has access to get into that aquifer. So when we pull out of these confined aquifers, we use that water up way quicker than it can actually recharge back into it due to rainfall. And so we tend to drain those out much quicker. Okay, this cone of depression idea, it's in your book. I've never seen it on the AP test. Don't know that you'll actually really see it, but it's always sort of a good idea to have at least an experience and exposure to it. So here we have a picture of our aquifer with our water table. We've got two little houses here that have wells dug to gain the water out of that aquifer for their use. But then they built a farm. And this farm needs water for all these crops. And so they built a really, really deep well to be able to access lots of water. And here are after our after picture, we have lots of pretty crops here. However, because they have pumped so heavily out of this large well to water those crops, it has drained our aquifer out. And so now, because of the depression this makes, or this cone of depression, these two houses, their wells have gone dry. And this is very typical of what happens. We need lots of water for farming, and so we drain a lot of our aquifers due to this. Okay, one of the other issues that we have with building wells is if you build a well by the ocean, We get lots of salt water that can then get into your well and your drinking water. Normal conditions, that freshwater flow in your groundwater is able to keep the salt water out. But the minute you drill that well and you start pumping that fresh water out of there, that then opens up space and leaves space for this salt water to flow in, and then you start pumping salt water in through your pipes and into your drinking water. Not good. Some more vocabulary that you guys need to know. Oligotrophic just means a river, stream, body of water that has very low nutrients. The nutrients in particular that we look at is phosphorus and nitrogen. Remember, phosphorus cycle, it's all in rock. We pull it out, we put it in our fertilizers. Why do we do that? Because it helps plants grow, and so does nitrogen. We'll talk about this a lot more, this idea a lot more. Mesotrophic just means that it's a moderate level, and then eutrophic is very high levels. You've probably heard me use the term eutrophication a lot in class. We're going to talk about that a lot more when we do water pollution. It's a really, really big problem, particularly here in the Bay, that they're having. So we'll talk about that a lot more. Okay, yet again, another thing that I've never seen on the AP test, you probably won't see it, but the difference between a levee and a dike. I know you've all heard those terms, particularly with Hurricane Katrina, the levees failed. A levee is basically just a piece of embankment that they have built to separate two bodies of water. So this side here is a levee. It's separating this body of water from this one over here. A dike is just very similar, except it separates a body of water from the land. So over on this side is a dike. These are here to prevent erosion, to prevent flooding, and like with Hurricane Katrina, the levees broke, as this picture here shows, and so we had infiltration into other bodies of water and also up into the land, also massive flooding. All right, a lot of what we're going to talk about with this topic are dams. This is dams are sort of the biggest idea that they have in this unit. So here's a nice pretty dam that's built over this river. Dams are there to help. Most of the time we build them to help with flooding, but they can create more flooding, which we'll see here in the next slide. In this area back here behind the dam, that's what we call a reservoir, and we pull water from this for drinking, for household use, things like that. All right, so what are some pros and cons of dams? Well, they do control flooding downstream. A lot of dams are built because we have flooding downstream from the dam, and so when you build the dam, you can start fluctuating and controlling how much water runs downstream. A lot of our dams are built to provide electricity, hydroelectric, and we'll talk about that some more too in class, particularly when we do our energy unit. And it provides recreation because in that reservoir area you can do a lot of fishing and boating and things like that. Dams, as everything, causes problems. So even though you're controlling flooding downstream, you've now dammed up and pushed up the amount of water that's upstream, and so you start getting a lot of more flooding upstream than you had before. Because that dam is there, fish cannot migrate back and forth the way they used to, and so we have to build in some special things for that, and that causes problems, decreases evolution in genetics. Because of that flooding upstream, we can displace people and habitat. It causes lots of erosion. A lot of times on the sides of rivers are sometimes wetlands, and so you build that dam and you destroy the wetlands. Wetlands are like sponges. They soak up that extra water to keep flooding from happening. They also help filter the water and filter pollutants out of the water, so destroying them is a really bad thing. And dams are crazy expensive to build and to run, and so there's those problems also. Okay, so I mentioned that fish can't migrate. We do build sometimes these things called fish ladders, where the fishes can then swim up over top of the dam and get to the other side of the river. Doesn't mean that it's not their natural flow, so they don't always tend to naturally use these, but it does help, and we're working on this technology more and more. Okay, so if you're living in an area where there isn't a lot of water, let's say you live out in the Middle East, in Iran or Iraq, it's desert, there's not a lot of water there. And so you've got to find some source of water other than just the fresh water that's in some river and stream that doesn't really happen there, or through the rain, which doesn't really happen there much. So there's two processes. One is called desalination, This figure is trying to show you what it does. Basically what they do is they put water in a bin, they superheat it, all that fresh water evaporates, which they then collect, and it leaves the salt behind. Extremely expensive to do this because of all the heating that it takes, and not very energy efficient. The other thing that they can do is something called reverse osmosis. Remember osmosis from bio. So basically they put water in a container, they apply lots of pressure here, and there's a membrane. The membrane is big enough to allow water to flow through, but not the salt. And so then they collect the water on the other side. Much more energy efficient, but still quite expensive to do. All right, so if we're using all this water, what are we using it for? Where does it go? Well, the number one place is agriculture. Watering crops takes a lot of water, and there's a couple of different ways that we do this. There's a few shown here in this figure. There's one called furrow irrigation, where they build a trench, they put a big tube in it, and then they just constantly dump water onto the crops. Very inefficient. One of the big problems you'll see with this one, the flood irrigation and the spray irrigation, is you've constantly got water on the ground. If it's a hot day, all that water is evaporating out, so you're being extremely inefficient with that water. Also, these crops that are sitting here usually get flooded out, and the crops way over here don't get enough water, so this is not the best source of or best way of doing this. There's flood irrigation, where you just flood the whole field. Again, you're overwatering. Spray irrigation is a bit better. You've probably seen these maybe as you're traveling through some more farmland type areas, where they just spray throughout the day. It's good because then you can regulate what time of day you're spraying your crops, but again, not quite as energy efficient as we would like. The best one is what we call a drip irrigation, where there are these pipes that run out to the fields, and they just slowly drip water onto the plants, and hopefully the plants in the soil absorb it as it comes out, since it's a slow drip that comes out. We also use water for industry. This picture here is of a nuclear power plant, and we will talk about that more when we do energy, but lots of water used in nuclear power and other industries to run different machinery. And our third biggest one is our houses. You can see here Australia, Canada, and then us, so we're not the worst with our water use. But we do use a lot of water in our houses, and it's easy for us because we just turn the tap on and it comes right out and we don't think anything of it. What's the number one thing that in our house that we use water for? Flushing our toilets. And then bathing and laundry and cooking come behind that. So you're starting to see, if you go to Home Depot or to Lowe's, low flow shower heads and toilets that don't use as much water. The basins aren't as big. A lot of our washing machines are starting to use less water. Those front loader washing machines are less water. So we are coming up with new technology to focus in on this and help us use less water in our houses. But we have to be conscious of how much we're using, letting that spigot run, and turning on that faucet, and how much we are using out of that faucet to help too. Okay, so the future of water. Water is a big topic that a lot of people are having concerns over, and it's a hard one to solve because there's no saying who owns the water. Nobody really owns a waterway, and so who says what gets done with it, what gets dumped in it, how it's used, since there is no ownership over it? What are the rights behind it? This picture here, is a house that what they're trying to show is all of these plants. These are native plants. Obviously, this is a desert area that don't require as much water, things like cactuses and succulents. I have a good friend of mine who just moved back from the West Coast, from Southern California, and she was telling me that out there, if you rip up your grass and you plant water-resistant plants like this and local plants, that they actually pay you to do that because they're trying to reduce the amount of water that's needed in these areas that are very desert-like, that don't have a lot of access to water. Like I mentioned before, we have a lot of faucets and fixtures that are low flow that use a lot less water. This picture here, I think this is really cool. This is using what we call gray water. So above this toilet is a washing machine. This is from Germany, I believe. And so you wash your clothes in your washing machine, and then the water that's left over once you're done washing it then goes into the toilet, and you use that water to flush, because we don't really care if our water in our toilets is completely clean. It's not like we're drinking it. So we can use some of our water from some of our appliances that maybe not be completely clean to do things like flush toilets, maybe water plants, wash our cars, things like that that we don't necessarily